Hi everyone, Dr. Burns here with our second lesson in Chapter 11, Gases, where we will be discussing the ideal gas equation, gas mixtures, and reactions with gaseous reactants and products. Get your calculators out because we will be doing a lot of math in this lesson. So in our previous lesson, we talked about how pressure, volume, number of moles, and the temperature of gas all matter in determining each of those variables for a specific sample of gas, and how changing one will affect the others. And we talked about the four laws, the four gas laws: Boyle's law, Amundsen's law, Charles' law, and Avogadro's law, where we saw the relationships between pressure and volume, pressure and temperature, volume and temperature, and volume and number of moles. The ideal gas law combines all four laws to relate pressure, volume, temperature, and the number of moles of gas. So we define the ideal gas law by this equation here. PV equals nRT. Here, P is pressure, V is volume, N is number of moles, and T is temperature, which we've all studied in the previous lesson. A new variable in this equation is R. R is the ideal gas constant. So it is a constant variable which has a number associated with it, which we'll get to in the next slides. But its units are expressed in pressure, volume, moles, and temperature so that it can relate to all four variables of a gas. The ideal gas constant R is the proportionality constant, and its value in units depend on the units in which P, pressure, and V, volume, are expressed. So here are the various values of R. And you'll notice that their units for each value depend on the volume, the temperature, and the moles, but where they differ is in their pressure units. So we have some that are in ATM, torr, bar, and pascals. So that means whatever pressure is given in the problem, okay, whatever the unit is for that pressure, you have an R that can be used with that pressure. We have to make sure that the R has the correct pressure units so that the units cancel appropriately for that specific pressure. Now we aren't going to use these last two values of R because those are specific in more in Gen Chem 2 than they are in Gen Chem 1. So we're going to look more so at the first four where the pressure units are defined more clearly. I want to reiterate our concept of standard temperature and pressure, also known as STP. STP are a special set of conditions where the pressure is defined as 1 atm and the temperature is defined as 0 degrees Celsius or 273.15 Kelvin. We said previously that the volume occupied by 1 mole of an ideal gas is 22.4 liters, and now we can use our PV equals nRT equation to prove that. So at standard temperature and pressure, we know our pressure, we know our temperature, we've defined N as 1 mole, and now we can also define R. R would then be in units of atm to match our standard pressure of 1 atm. Therefore, plugging those values into PV equals nRT and solving for V, the volume, gets us 2.4 liters for the volume of 1 mole of ideal gas. So let's start to practice with our PV equals nRT expression. In this problem, we want to calculate the pressure in bar of 2,520 moles of hydrogen gas stored at 27 degrees Celsius in a 180-liter storage tank. So we're given here PV equals nRT, a bunch of our R values, as well as some conversions to go between a few different pressures in case we needed it. Well, we want to calculate the pressure in this problem in bar, and we have an R value that's already in bar. So if I use R that has a unit of bar already in it, as long as the units of my other variables are the same as that R value, so liters, moles, and Kelvin, those units will cancel out appropriately and we will be left with a pressure in bar and we wouldn't have to do any conversions. Now, if you wanted to practice your conversions, you are more than welcome to go with any R value that you feel comfortable with, and then getting the pressure in that R value and then converting to bar. So here we're going to define pressure is what we're looking for. P is a question mark. V is the volume of the moles, which is going to be 180 liters. N is defined as 2,520 moles. And T is originally defined as 27.0 degrees Celsius. But as with our other gas laws, we need to make sure that that temperature is in units of Kelvin. Now we can see why, because R is in units of Kelvin. So in order for our units to properly cancel, our temperature has to be in Kelvin, our moles have to be in moles, and our volume has to be in liters. So we always want to convert to match our constants. In this case, R is our constant. So we're going to add 273.15 to our 27 to get our temperature in Kelvin. And we get 315 Kelvin. So let's use these variables and let's plug them into our PV equals nRT expression. So we have P, which we're solving for. We have V, which is 180. Then we have N, which is 2520. And now we have R. We want to make sure we use the R that is in the same units as the pressure that we either have or that we want. So we are going to use 0.08314 for our R. We're then going to plug in our T, which is 315 Kelvin. And now we want to solve for P. So in order to isolate P, I'm going to divide both sides by 180. And we get pressure is equal to, well, I'm going to do 2520 times 0.08314 times 300.15. And then I'm going to divide that by 180. I get a pressure of 349.36 bar. With sig figs, this would come down to 3, so this would be 349 bar for our pressure. Let's try another one. How many moles of gaseous boron trifluoride are contained in a 4.3410 liter bulb at 780 Kelvin if the pressure is 1.220 atm? Well, let's define our variables and see what conversions we need to do, if any. So we have first pressure, volume, moles, and temperature. So our pressure is given as 1.220 atm. Our volume was given as 4.3410 liters. Our number of moles is what we are looking for. And our temperature was given as 788.0 Kelvin. So we're already given our temperature in Kelvin, meaning that we have all of our variables in the proper units. We can double check this by looking at our value of R. The value of R that we're going to want to use is the one that has ATM in it, because our pressure is in ATM. So we need to make sure our volume is in liters. It is. We're going to find our value of moles in moles, so that's good. And our temperature is in Kelvin, which it is. So we have matched all of our variables and their units to the R value, meaning when we plug everything in, all of the units will cancel appropriately. So let's plug it in and solve. We have P, which is 1.220 ATM, times the volume, 4.3410, is equal to N, which we're solving for, times the R that we chose, 0.08206, times the temperature, 788.0. And now we solve. So to solve for N, we're going to divide both sides by 0.08206 times 788. If you wanted to simplify those first, feel free. So N is going to be 1.220 times 4.3410, end parenthesis, divided by 0.08206 times the temperature, 788. So I get a number of moles of 0.0819. And I think with the sig figs, this should have 4, so we'll add that 0 at the end. Moles. Now the interesting thing with solving for moles is the question could have also asked how many grams of boron trifluoride are there. So if we did need to go to grams, we could then convert this to grams using our molar mass. Because even though a gas is very different from a solid and a liquid, it doesn't have intermolecular forces, it still has a mass. So we could still take the number of moles of a gas in a container and we could still calculate its mass using the molar mass of the gas itself. So keep that in mind for problems that you may see on your homework for this lesson. Let's do another one. A chemist is preparing to carry out a reaction at high pressures that requires 5.50 moles of hydrogen gas. The chemist pumps the hydrogen into a 12.4-liter rigid steel container at 25.0 degrees Celsius. To what pressure in kPa must the hydrogen be compressed? I want you to try this problem independently, but in order to do that, I want to get you a proper value of R on the screen for you to reference, which I believe I have up here, yes. So here we have PV equals nRT as our equation. And for R, we have a value of 8.314 liters times kPa times moles to the -1. Kelvin to the -1. Okay, so there's your R value for you to use. So please pause your video and solve this problem independently. To start this problem, the only variable we need to change in terms of units is our temperature. So we need to take T and go from 25 degrees Celsius and add 273.15 to it in order to convert it to Kelvin. 25 plus 273, we get 298.15 Kelvin. So now we are prepared to plug in our values and solve for pressure. So we have P, which we're solving for, times the volume, which was given as 12.4 liters. That's equal to the number of moles, 5.50, times the R value that I gave in kilopascals already, which is 8.314, times the temperature of 298.15 Kelvin. Again, if you're ever concerned about if your variables are correct, we can just double check our R value to make sure that everything is in the proper units and that they're plugged in correctly into our equation. If you plugged them in correctly and they have the correct units, then the units will cancel. So now we're going to solve for pressure. So I'm going to divide both sides by 12.4 in order to isolate pressure. So we get pressure is equal to 5.5 times 8.314 times 298.15, all divided by 12.4. So we get a pressure of 1099.47, and this is going to be in pressure units of kPa. Now for this problem, we should have three significant figures, so this would simplify to 1.10 times 10 to the 3 kPa. If you are having trouble with the algebra portion of these types of problems, like you tried this on your own and did not get the same answer, it's most likely coming down to an algebra and rearrangement problem. So again, as I've said in our previous lesson, if you need to, rearrange the equation before plugging in variables. So for this one, we would have PV equals nRT, and in order to solve for pressure, we would divide both sides by the volume. So that would be pressure is equal to nRT over volume. Then once you've rearranged your equation and you have your variables in the right spot, then plug in your numbers so it's easier to rearrange than if you were to plug it in originally, because sometimes those numbers can get mixed up. Okay, here's another one. I want you to try this one independently. Calculate the volume in liters of a 124.3 grams sample of carbon dioxide at STP. For this one, we need the R value for ATMs, which was 0.08206 liters times ATM per mole Kelvin. So that's R. We have PV equals nRT. Okay, so try this one independently. To solve this problem, we need to use a few bits of prior knowledge in order to start us out. The first being STP. STP tells us that the pressure is equal to 1.0 atm and that the temperature is equal to 273.15 Kelvin. So we know P and we know T we're looking for V. We always know R because it's a constant. The other variable we need to find now is N. We're not given a value for moles in the problem directly. However, we are given grams of carbon dioxide, meaning we are able to go from grams to moles using our molar mass. So that's something that we've done multiple times now throughout this course. So to start off that problem, we need to take 124.3 grams of carbon dioxide, and we need to find the molar mass of carbon dioxide. So carbon's molar mass, 12.01, and we're going to add to that 16 times 2 because the molar mass of oxygen is 16 and there's 2 of them. So the molar mass of carbon dioxide is 44.01 grams per 1 mole. So we'll divide by that value. In order to have grams cancel and be left with moles of CO2. So we'll take 124.3, divide by 44.01, and we get 2.8244 moles of CO2. So now we have moles, we have P and we have T, and we can now solve for V. So let's do that. Our pressure was 1 atm. We're solving for V, which is the volume. Our N we just calculated as 2.8244. The R value that we need is 0.08206, and the T value comes from STP of 273.15. Okay, solving for B or V, we don't need to do anything. That 1 is just going to cancel itself out because it's 1, so we just need to take 2.8244, multiply that by R, 0.08206, times the temperature, 273.15. So that gives us a volume of 63.308 liters. And with sig figs, this would be 63.31 liters. We get 4 sig figs from the value of grams in our problem. Next up, I want to talk about gas mixtures. So we've talked about individual gases and how they relate to the gas laws. So those are typically talking about one gas itself and how changing the variables will change the gas, or how we can find the individual variables for a specific sample of gas. Now we want to talk about 2 or more gases that are forming a mixture. When 2 or more gases are placed in a container, each gas behaves as though it occupies the container alone, so it doesn't even acknowledge the other gas present. And this makes sense with what we know about gases not having intermolecular forces. Gases are so far apart from each other, the individual molecules are so far apart that they don't have intermolecular forces. So they don't have intermolecular forces between themselves, 2 gas molecules of the same type, but then they also don't have intermolecular forces between 2 gas particles of different types. So let's consider a sample of 1 mole of nitrogen gas in a 5.0 liter container at 0 degrees Celsius. We can plug that into our PV equals nRT equation and solve for the pressure of that gas in that container, and we can see that it comes out to 4.48 atm. We can then add 1 mole of oxygen gas to the same container. It would be under the same conditions and therefore would exert an additional 4.48 atms of pressure on the container. There's still 1 mole of it. It's in the same container which has the same volume, and they're both at 0 degrees Celsius. So the individual pressures of each compound is referred to as the partial pressure. So because they're mixed together, the pressure is made up of the pressure of one type of gas as well as the pressure of the other type of gas. So the total pressure of the mixture is the sum of those partial pressures. So the pressure of the nitrogen gas plus the pressure of the oxygen gas. So we can add those up and we can see that the total pressure of the entire container with nitrogen and oxygen gas both in there is equal to 8.96 ATMs, which is the addition of 4.48 to 4.48. So we took the individual partial pressures and added them up. We call this Dalton's law of partial pressures, and this states that the total pressure exerted by a gas mixture is the sum of the partial pressures exerted by each component of the mixture. So we have an equation here, P total, which is the total pressure, equals the sum, okay, this is a sum sign for those who don't know, of the individual partial pressures. So if we had a mixture of water, HCl, CH4, and H2 all in the same container, the total pressure would be equal to the pressure of the water plus the pressure of the HCl plus the pressure of the methane plus the pressure of H2. If I were to add more gas to that container, then I would increase the total pressure because its partial pressure would add to that sum overall. So, to reiterate, each component of a gas mixture exerts a pressure independent of the other components. The total pressure is the sum of the partial pressures, which is what this is showing here. You have these purple ones, which are exerting, I don't know, a quarter of the amount on here. And then you have the yellow ones that are exerting about half on there as well. So when we combine them together, their pressures combine to about 3/4 of the total there. So let's practice this. Here, a 5-liter vessel contains 0.041 moles of helium, 0.21 moles of neon, and 0.0922 moles of argon gases, all at 25 degrees Celsius. Calculate the partial pressures for each component in the container and the total pressure of the vessel. So what we're going to do here is similar to what we saw with nitrogen and oxygen gas in our previous examples, where we want to solve for pressure using nRT over V. I just rearranged our PV equals nRT equation to solve for pressure. Except each n is going to vary for each of these calculations. So let's start with helium. The pressure of helium is equal to the mole value, which is 0.041, times R. Let's do our partial pressures. It doesn't tell us a unit, so let's choose ATM. I just really personally like ATM. It's my favorite pressure unit. So an R value for that is 8.08206 liters ATM per mole Kelvin. Okay, so we'll do ATMs for our pressures here, 0.08206 times the temperature, which is going to be 25 plus 273. Okay, so that's 298.15. and then we'll divide by the total volume, which is 5 liters. So let's do that. 0.041 times 0.08206 times, what's 25? That's 298, I'll just plug it in, plus 273.15, which we then divide by 5. Okay, so we get a pressure of helium of 0.20062 atm. I'm going to leave a few extra decimal places just so that when we add for the total pressure, we have all those decimal places. But since we also asked for the individual partial pressures for sig figs, this will be 0.200 atm. Okay. So then we have the pressure of neon. So it's the same setup, except now we're going to swap out 0.041 for 0.121. But the R is the same, and the T is the same. 25 plus 273 is 298, and the volume is the same. So we get 0.121 times 0.08206 times 298.15 divided by 5. And we get 0.59208 atm. With sig figs, this becomes 0.592 atm. And our last one is argon gas. So we have the pressure of argon is equal to the mole value, which is 0.0922 times everything's the same. Okay, so we get 0. Times 0.08206 times 298.15 divided by 5 for the volume. So that's 0.451157 atm. With sig figs, 0.451 atm. Okay, so those are the individual partial pressures for this problem. Now we want to take all of those individual partial pressures, add them up to find the total pressure. So we're going to take 0.20062 plus 0.59208 plus 0.451157, and we get 0.20062 59208 451157. We get a total pressure with 3 sig figs of 1.24 atm as the total. Okay, let's do another one. Determine the partial pressures and total pressure in a 2.50 liter vessel containing the following mixture of gases at 15.8, that should be a degrees Celsius. We have 0.0194 moles of helium, 0.0411 moles of hydrogen, and 0.169 moles of neon. So this is very similar to our previous problem, so let's get our R up there for you to have, 0.08206 liters atm Kelvin. So what I want you to do now is pause this video and try this problem independently to find both the partial pressures and the total pressures of this sample of gas. The setup is exactly the same as we saw in our previous problems. So we just choose each variable. Let's do helium first. And we just plug in their mole value, 0.0194 times R times the temperature, which would be 15.8 plus 273.15 to get 288.95 Kelvin, divide by the volume of 2.50 liters. So we just plug that in, 0.0194 times 0.08206 times 288.95. We get, and divide that by 2.5, there we go. 0.183999 to ATM there. Okay, next up is hydrogen. All we're changing is the mole value because that's the only thing that changes in all of our sample, but everything else is the same. Okay, so we get 0.0411 times 0.08206 times 288.95, all divided by 2.5 liters. So that is 0.389813 ATM. Next up, we have the pressure of neon. So same setup, just a different mole value. Okay. (169) times R times the temperature divided by the volume. So we get 1.60288. Okay, so let's see, we would have what? 3 sig figs for these, so 0.184 for our individual partial pressure, 0.390, and 1.60. Then to find our total, we're just going to take those individual ones and add them up. 18399 plus 0.389813 and 1.60288 to get 2.1718 with sig figs. And that is our total. Okay, let's see what's our next one. Determine the number of moles of each gas in a mixture of methane and C2H6 in a 2-liter vessel at 25 degrees Celsius and 1.5 ATM when the partial pressures of CH4 is 0.39 ATM. So let's think about this problem. We have PV equals nRT. We want to solve for N now instead of P. So we're going to say that N is equal to PV over RT. So we need to have the individual partial pressures for each component. We're given the total pressure, and we're given the partial pressure of CH4, but what we don't know is the partial pressure of C2H6. So what I want you to do is pause your video and think of how you would find that partial pressure of C2H6 given that you have the total pressure and the partial pressure of CH4. Then once you find that partial pressure, you can now calculate the number of moles for both CH4 and C2H6. So try that. Pause your video and try that now. So remember that the total pressure will be equal to the pressure of CH4 plus the pressure of C2H6. So since we know the total pressure is 1.50, and we know the pressure of CH4 is 0.39, we can solve for the pressure of C2H6. So we just take 1.5 and subtract off 0.39 to get the pressure of C2H6 to be 1.11 atm. So now that we have the pressures, we can solve for the number of moles for each of these. So the number of moles for CH4 is equal to its pressure, which is 0.39, times the total volume of 2, divided by R, which in this case is 0.08206, and the temperature, which is 25 plus 273, 298.15 Kelvin. So we get 0.39 times 2 divided by 0.08206 times 298.15. So the number of moles of CH4 is equal to 0.0318 with 3.919 with sig figs. There we go. We can do the same for C2H6, so we have N of C2H6, and its pressure was 1.11 atm, but everything else is the same. The volume's the same, the R is the same, and the T is the same. So now it's just plugging it in. 1.11 times 2 divided by 0.08206 times 298.15. And we get number of moles of C2H6 to be 0.0907. And those are the final answers for that problem. Now let's take this one step further and start discussing mole fractions. The relative amount of the components in a gas mixture can be specified using mole fractions. So here's the expression for a mole fraction. This is chi, Greek letter chi, and it is the mole fraction, just saying that's just how we represent mole fractions. And it's equal to the moles of a certain component, N sub I, divided by the total moles in the sample. So it's like a part over a whole in our gas mixture. So if I have 4 moles of gas, And I know 1 mole is made up of hydrogen gas, 2 moles is neon, and 1 mole is argon. Well, we could find that there is 1/4 for a fraction of hydrogen, 2/4 for a fraction of neon, and 1/4 for a fraction of argon. We could simplify 2/4 to 1/2, that's totally fine. Okay, it's just the part over the whole. There are a few things to remember about mole fractions. The mole fraction of a mixture component is always less than 1, right? It can't be more. You can't have more of the gas, of a specific type of gas, than the total gas in the sample. That wouldn't make sense. Okay? I can't have 4 moles of gas and 6 moles of those being hydrogen. That wouldn't add up correctly. So it'll always be less than 1. So here we have 0.25, 0.25, and 0.5. The next thing is that the sum of the mole fractions for all components of a mixture is always 1. So in our example, we have 0.5 plus 0.25 plus 0.25 plus 0.5, which all equals 1. And the final thing to remember about mole fractions is that they are dimensionless. Okay, we have 1 mole divided by 4 moles. Our units of moles will cancel on the top and the bottom, meaning that this is totally dimensionless, also known as unitless. It's another way of saying unitless. Dimensionless and unitless are the same thing. Okay, so let's use some mole fractions. We can relate the number of moles and the pressure because we can say that in a mixture, the number of moles and the pressure at which that sample exerts on the overall container are proportional to each other as long as the temperature is held constant and the volume remains unchanged. So we could also have a pressure fraction. So here's our expression for mole fractions here, but instead of Ni and P and N total, we have Pi and P total. Okay, so your pressures can have a fraction in the same way that the overall moles do. So like we saw before, we had 0.39 atm of methane over the total 1.50 atm overall. That would be a pressure fraction. The other one came from the 1.11 from the C2H6 over the total. Okay, so we can think of mole fractions and pressure fractions as the same thing. If we know the specific fraction, we can then multiply it by the total value and get the individual value back, right? Because the chi, I'm going to use it for pressure because we have it here, I have P sub I over P total. If I multiply it by P total, I can get P sub I. So if I don't know how the mole fraction was calculated, okay, then I can use that to find the individual piece. On the other hand, if I know the mole fraction for my pressures and I wanted to find the individual amounts of moles, I could do that as well. So let's look at how we can use these. I have a few practice problems that explore both finding mole fractions as well as how we can apply that to find the individual components as well. So, what is the mole fraction of O2 in a mixture of 0.756 moles of nitrogen, 0.189 moles of oxygen, and 0.0132 moles of carbon dioxide? Well, I want to find N sub I of oxygen, so that's what we're looking for. So we need to find the N total first and then divide. I should say this wouldn't be the n sub I. I want to find the chi. There we go. That's a better representation. I want to find the mole fraction of oxygen. So what we need to do, we need to calculate N total first. So we need to add up all of those mole values. 0.756 plus 0.189 plus 0.0132. 0.756 plus 0.189 plus 0.0132. So our N total is 0.9582 moles. If we want to find the mole fraction of specifically oxygen, we need to take the N sub I of oxygen, which is this guy, which I'll now label correctly with N sub I, okay, and we want to find the chi from there. So chi is equal to N sub I, 0.189 moles, divided by N total, 0.9582 moles. So we take 0.189 divided by our total to get a mole fraction of 0.19724. With sig figs, this would come out to 0.197. And that is the mole fraction. There are no units on it. If we wanted to double check our work, we can find the mole fractions for both nitrogen and carbon dioxide and make sure that all of those chi's add up together, which is totally fine. You can do that if you want, or you can just trust that you know what you're doing at this point, and that as long as you're showing that you added up all of those moles and did the part over the whole, that you got the problem correct. Okay, so here's one where we can use our mole fractions to find the individual pieces. So, we want to know the partial pressure of carbon dioxide in a gas mixture that contains 4.10 moles of oxygen, 2.38 moles of nitrogen, and 0.917 moles of carbon dioxide, and has a total pressure of 2.89 atm. So we want to find the partial pressure of this. Okay, so this is P total. And we want to find the partial pressure, PI. Spell total right. So we want to use this equation here. Because I want to find PI, I know P total, I just need to find a fraction. Now chi, we said, can either be a mole fraction or a pressure fraction. I don't have any pressures given here, or pressures that would allow me to find a pressure fraction, but what I do have is mole fractions, and mole fractions are equal to pressure fractions. So if we know the mole fraction, we can find that that is the pressure fraction. So we'll go about finding N total and N and chi for the moles, and then use that to find the partial pressure. So our N total is going to be 4.10 plus 2.38 plus 0.917. So you have 4.1 plus 2.38 plus 0.917. So our N total is 7.397 moles. Chi, our mole fraction, is now going to be the part over the whole, and in this case it's going to be CO2. So 0.917 moles of CO2 make up the total 7.397 moles. And we get a mole fraction of 917 divided by 7.397. We get a mole fraction of 0.12397. Okay, so we have chi, we have P total. We can now take chi 0.12397, multiply it, not even going to show an x, I'm just going to show it in parentheses, multiply it by 2.89 ATM. So we do that times 2.89. We get the partial pressure of CO2 to be 0.358 ATM. So because the moles and the pressure are proportional to each other as long as temperature and volume are remaining constant and unchanged, we can use our mole fractions to help us find our partial pressures, because a mole fraction is equal to our partial pressure. They make up the same kind of ratio, whether you're looking at moles versus pressures. Let's try another one. A mixture of gases contains 0.3 moles of CH4, 0.25 moles of C2H6, and 0.29 moles of C3H8. The total pressure is 1.50 ATM. Calculate the partial pressures of all of the gases. So pause your video and try this problem. Find your mole fraction. Once you have your mole fraction, use that to find the individual partial pressures. The first step that you're going to want to do is find your total moles. So N total is going to be equal to 0.31 plus 0.25 plus 0.29. So we get 0.85 moles total. So now we're going to take those chi values. I'm going to simplify this and just put it right in my equation instead of solving for them individually. We're going to find chi multiplied by the total pressure of 1.5, and that will give us the partial pressure. So for pressure of, let's do CH4 first. We get a chi of, let's see, 0.31 divided by 0.85. which we're going to multiply by the total pressure, 1.5. So I just kind of simplified what I did in my previous example. This is chi. So we take 0.31 divided by 0.85 and then multiply that by 1.5. So that would give me a partial pressure of, for CH4 of 0.55 ATM. Next up, we'll do the same thing for C2H6, except now its partial is going to be 0.25 over 0.85, but we're still multiplying that by the total pressure of 1.5. 0.25 divided by 0.85 multiplied by 1.5. We get 0.44 ATM. And finally, we have the partial pressure of C3H8, and that's going to be equal to 0.29 divided by 0.85, which will be multiplied by the total pressure. 0.29 divided by 0.85 multiplied by 1.5, and we get a partial pressure of 0.51 ATM. Now we can add these up and just double check our work. 0.55 plus 0.44 plus 0.51, and we get a total pressure of 1.5. So we can use our mole fractions to find our partial pressures. Here's one from your ALEKS homework. N2 gas is mixed with oxygen gas, and the sketch below shows a representation sample of the mixture. The total pressure of the mixture is measured and found to be 1200 torr. Calculate the mole fraction and the partial pressure of each gas in this mixture and round your answers to 4 significant figures. Okay, so the way that we're going to go about this is still going to be the same. We're going to find the mole fractions and use that to find the partial pressure. But we can use our concept that molecules are proportional to moles in order to do this. So if we know the number of molecules total, and we know the number of individual molecules, we can find the chi, the mole rate, the mole fraction, okay? Because molecules and moles are interchangeable. So let's count up our total molecules. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 molecules total. So that's going to be our denominator in each of these. Nitrogen is blue. So nitrogen, how many molecules of those 20 are made up of nitrogen? 1, 2, 3, 4, 5. So nitrogen's mole fraction is going to be 5 over 20. And your ALEKS homework wants you to find the decimal for this, so we are going to do 5 divided by 20. So 0.25. For oxygen, oxygen is red, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oxygen, there's 15 out of 20. So we do 15 out of 20, and that's 0.75. So those are your mole fractions, 0.25 and 0.75 for each of those. Now we can use those mole fractions to find the partial pressure. We know our P total is equal to 1200 torr. So for nitrogen, we're going to take 0.25 and multiply it by 1200. So the partial pressure with respect to nitrogen is 300 torr. And for oxygen, we'll do the same thing, but use 0.75 as its mole fraction times 1200. So its partial pressure is 900. We can add these up. This adds to 1200, check. And we can add these up. They come to 1, check. So we know we did both of those correctly. So when you see this on your ALEKS homework, that's what you need to do. Make sure that you are equating molecules and moles together. Okay, and for our last section here, we're going to talk about chemical stoichiometry and gases. We've talked about stoichiometry before when we were talking about balanced equations and calculations we can do with balanced equations, the different types of chemical reactions. We've done titrations, and we've done molarity conversions, as well as gravimetric analysis equations, all of these using stoichiometry or mole-to-mole ratios. So I'm going to write that here because we need to remember mole-to-mole ratios. So it's the quantitative relationship between reactants and products and chemical reactions. We have looked at measured quantities of reactants and products of solids and solutions, and the same can be applied to gases. So let's look at the example. Consider the following balanced equation. Determine the volume of oxygen gas formed from the decomposition of 5.36 grams of mercury oxide at a pressure of 0.975 atm and 23 degrees Celsius. In this problem, we are going to combine our knowledge of mole-to-mole ratios with our new knowledge of PV equals nRT, the ideal gas equation. Because if I want to find the volume of a gas, and I'm given pressure and temperature, we can use the mass of one reactant and convert to moles of the gas. Okay, we know how to convert from one reactant to a product. We've done that before. Now we're going to use that mole of product and we're going to plug it into our PV equals nRT to solve for volume. So I have a little kind of chart here, or some steps here for this. So the first thing that we're going to want to do in this problem is we're going to first want to convert our mass of solid to moles of solid. Okay, we know how to do that. We can convert mass to moles. We know how to do that. So let's see, we have mass 5.36 grams, and we can use the molar mass of mercury oxide, which is 216.59 grams per 1 mole. We can find that from the periodic table, that molar mass. So we'll take 5.636, and divide it by 216.59. Okay, we get 0.02477 moles of HGO. I can't use this value in PV equals nRT because HGO is a solid. The only thing that I can plug into PV equals nRT is the mole value of a gas. So what we have to do next is use our mole-to-mole ratio to find moles of gas using the balanced reaction. So from my balanced reaction, for every 2 moles of mercury oxide that I react, I get out 1 mole of oxygen gas. So we can set up our equivalency. 2 moles of HGO give us 1 mole of O2. So we just take our mole value and we divide it by 2 to get 0.012373. And that is moles of O2. So the 0.012373 moles of oxygen can now be used in PV equals nRT. Because it's a mole value of a gas. And that's very important. It has to be the mole value of the gas itself. So we're going to use that moles. We're going to plug in moles for of gas into PV equals nRT to solve for volume. So we'll do that here in blue. So we'll take P, which is 0.975. We're solving for volume. We know moles, we just solved for that. It's 0.012373 times R. Let's see, my pressure is in ATM, so I'm going to want to use R in ATM, which is 0.08206. times the temperature, which would be 23 plus 273.15 to convert it. So we take 0.01273, multiply that by 0.08206, and multiply that by 23 plus 273.15. And then we divide that by 0.975 to isolate the volume, to get a volume of 0.308 liters. It's liters because R dictates our volume right there. So that is the volume of gas that is created when mercury oxide is reacted into mercury and oxygen gas. We get 0.308 liters of oxygen gas. Okay, so that's how we use our previous knowledge. So let's see. Step 1 was previous knowledge, and step 2 was previous knowledge. We did that in our last 2 chapters. Now we're utilizing our new knowledge here in our 3rd step of PV equals nRT in order to solve for the volume of a gas given the moles of a gas. Okay, let's try that again. In the fermentation process, yeast converts glucose, C6H12O6, to ethanol, C2H5OH, and carbon dioxide, CO2. What volume of carbon dioxide measured at 745 torr and 25 degrees Celsius can be produced by the fermentation of 10 grams of glucose? So what I want you to do for this problem is to pause your video and walk through this. I will give you the R for torr so you don't have to convert. So let's see, R for torr is 62.36 liters times torr per mole Kelvin. So there's R there. You could also convert torr to ATM. You could do that as well and use the other R. Really, whichever route you take is fine. Make sure you convert your temperature to Kelvin and follow our little steps here. Convert mass to moles, use a mole to mole ratio, and then plug in the moles into PV equals nRT. Remember, we have to get to moles of CO2 because that's the gas. The only mole value we can plug into PV equals nRT is that of a gas. So pause your video and try this problem independently. The first step we're going to want to do is convert our mass of glucose to moles of glucose. So to do that, we're going to start with 10 grams of glucose, which I'll just call glue, and we're going to divide it by its molar mass of 180.16 grams in 1 mole. So we'll take 10, divide it by 180.16 to get 0.0550506 moles of glucose. So we did step 1. Step 2, we want to use our mole to mole ratio to find the moles of the gas. So for every 1 mole of glucose that I put in, I get out 2 moles of carbon dioxide. So we'll take 1 mole of glucose on the bottom so that glucose cancels, and 2 moles of carbon dioxide on top so that we're left with moles of carbon dioxide. So we'll multiply that by 2. And we get out 0.11101 moles of CO2. This is now the mole value that we can use for step 3 to plug into PV equals nRT to solve for volume. So our pressure is 745 torr. Our volume is what we're solving for. N is what we just solved for, 0.11101. R was given as 62.36. And T is 25 plus 273, that's 298.15 Kelvin. So we take 0.11101, multiply that by 62.36, and multiply that by 298.15. To solve for volume, we then divide both sides by 745, and we get that the volume is equal to 2.77 liters with 3 sig figs on there. So that is the volume of CO2 gas produced. So again, step 1, previous knowledge. Step 2, previous knowledge. Step 3, plugging in the mole value with our new knowledge of PV equals nRT, because the mole value we get out is that of a gas, and we can measure, instead of moles of gas, the volume of gas. Let's do some more practice. Here's a problem. Given the following reaction, H2 gas plus chlorine gas goes to hydrogen chloride gas, how many liters of hydrogen gas are needed to react completely with 5 liters of chlorine gas at STP? How many liters of hydrogen chloride gas is produced in the reaction? Okay, so here's one that we have to remember from our previous lesson. We said in Avogadro's law that moles and volume are directly related. So through Avogadro's law, we can take volumes of gas and we can convert to the volume of another gas using our balanced equation, because we can say that this is 1 volume of hydrogen gas and 1 volume of chlorine gas react to form 2 volumes of hydrogen chloride gas. So we can also be given a volume of gas and need to find the volume of another gas in the reaction. In this case, treat the units of liters the same as moles. The gases are at the same pressure and temperature, so volume is equal to moles. So our mole to mole ratios are turning into volume to volume ratios. So let's try that. So let's see, how many liters of hydrogen gas are needed to react completely with 50 liters of chlorine gas? So we have 50 liters of Cl2, and from our balanced equation, 1 volume of Cl2 is equal to 1 volume of H2. So we'll say 1 liter of Cl2 is equal to 1 liter of H2. So that gives us 50 liters of H2. Now you could go about this the same way we did our previous problems, okay? You would just start off the problem, instead of converting mass to moles, you would use the liters that you start with, liters of chlorine gas, plug that into PV equals nRT, get out moles of chlorine gas, use your mole to mole ratio to convert to hydrogen gas, then use that moles to then plug back into PV equals nRT. But since you're plugging the same pressure and temperature values into PV equals nRT, it's almost like doing the same thing twice. So you can do it the other way if that makes more sense to you, but you could also do it this way, where you could just use liter to liter ratios instead of mole to mole ratios. Okay, so the other question was how many liters of hydrogen chloride gas is produced in this reaction? Well, we start with our 50 liters of Cl2, and we can use our mole to mole ratio again. Instead, this is for every 1 liter of Cl2 that we use up, we get out 2 liters of HCl. So we take 50 liters of Cl2, multiply it by 2 from our mole ratio, and we get 100 liters of HCl created. So that's a way that we can use our mole to mole ratios as liter to liter ratios. But just keep in mind that it has to be between gases. You have to be going from a gas to a gas. If you're trying to go from a solid to a gas, you cannot do it this way. Okay, let's look at this problem. Given the following reaction, when black gunpowder explodes, solid potassium nitrate, solid carbon, and solid sulfur react with each other to form nitrogen gas, carbon dioxide gas, and solid potassium sulfide. If the original mixture contains 50 grams of potassium nitrate, what volume of carbon dioxide is produced in the reaction at 0.965 atm and 23 degrees Celsius? So here we're starting with a mass of solid potassium nitrate, and we want to find the volume of a gas. So just like we did before in our previous examples with our 3 steps. So try this problem independently. The first step in this problem is to convert from mass of solid to moles of solid. So we're going to take that 50 grams, pencils help, 50 grams of potassium nitrate, KNO3, and divide by its molar mass of 101.10 grams to get moles out. So 50.0 divided by 101.1, we get 0.49456 moles of KNO3. Our next step says to convert from moles of solid to moles of gas, and our gas here is going to be CO2. So we can go 16 moles of KNO3 produces 24 moles of CO2. So we'll take that, we'll multiply it by that ratio of 24 divided by 16, and we get out 0.74184 moles of CO2. So again, up until this point, this is all prior knowledge. We know how to go from grams to moles of a compound, as well as from moles of one compound to moles of the other compound through a mole to mole ratio from our balanced reaction. Now what we do with this mole value of CO2 is what our new knowledge is telling us, which is to plug that into PV equals nRT in order to solve for volume, because we can think of gases in terms of volumes rather than moles. So PV equals nRT tells us that the pressure is 0.965 atm times the volume, which we're looking for, is equal to N, which is the moles, which we just solved for, of 74184, times R. R for ATM is 0.08206, times the temperature of 23 plus 273.15, convert that to Kelvin. So we take 0.74184, multiply that by R, 206, there we go, times 23 plus 273.15. Then we divide that by 0.965 to solve for volume. and our volume comes out to be 18.7 liters of carbon dioxide gas produced. So when we take 50 grams of potassium nitrate, we create carbon dioxide, and the exact amount is 18.7 liters of carbon dioxide. Let's keep practicing. This one we're going to work backwards. So, given the following reaction, how many grams of solid lithium must be added to liquid water in order to obtain 15 liters of hydrogen gas at 65 degrees Celsius and 2 atm? So we're now looking for the mass of a solid given the volume of a gas. So we're going to work backwards. Our first step tells us to use PV equals nRT to solve for moles of gas. Once we have moles of gas, we're going to convert to moles of solid in step 2 using our mole to mole ratio. And once we have our moles of solid, we can convert moles to mass using the molar mass of that solid. So the same thing that we've been doing, just now working backwards. So I want you to try this problem initially on your own. So start with our steps, our 1, 2, 3 there, and see how far you get. If you get stuck, come back to the video and we'll go through it together. The first step to our problem is to plug in our volume of gas into PV equals nRT. So P is going to be 2.0 atm. We know our volume, that's 15 liters. We're solving for N of gas. We don't know that yet, but we do know R, 0.08206. And we know the temperature, 65 plus 273.15 to convert to Kelvin. So we can solve for N by taking 2.0, multiplying it by 15, and dividing that by R, 0.08206, multiplied by the temperature, 65 plus 273. There. So just to show that we have PV equals nRT. To solve for N, I just divided both sides by RT. So we get N is equal to PV over RT. Again, if it's easier for you to rearrange the equation before plugging it in, feel free to do that as well. Okay, so we get an N value of 1.08114, and that is going to be moles of hydrogen gas, so H2. So that completes step 1. We found our moles of gas. We now want to use a mole to mole ratio to find the moles of solid. So we're going to take that 1.08114 moles of H2, and we want to convert that to our solid, which is solid lithium. So for every 1 mole of lithium, I get out 1 mole of hydrogen gas. So 1 mole of hydrogen gas is produced from 1 mole of lithium. So that equals 1.08114 moles there. once we have moles of lithium, we can then use the molar mass of lithium solid, which is just from the periodic table, to find the mass. So 1 mole of lithium has a mass of 6.94 grams. So we'll take that and multiply it by 6.94, and we get out 7.50 grams of lithium. So we did step 2 with our mole to mole ratio here, and then we converted moles of solid to mass using the molar mass here. So we need 7.50 grams of lithium to produce 15 liters of hydrogen gas. We have a similar problem here. Given the following reaction, if 250 liters of hydrogen gas are used to reduce copper 1 oxide at STP, what mass of copper is to be expected? So we're starting with hydrogen gas here, and we're converting to copper solid. So use the same steps that we used in our previous problem, which are right here on the screen, in order to solve for the mass of copper. The first step is going to be plugging in our volume of hydrogen gas into PV equals nRT. Remember that STP tells us that our pressure is 1 atm and 273.15 Kelvin. So pressure is going to be 1. The volume is 250, which is equal to N, which we're solving for, times R, 0.08206, times the temperature, 273.15. So we solve for N. We're going to do 250 divided by 0.08206 times 273.15. So we get the number of moles to be 11.1534 moles of hydrogen gas. So that's step 1. Now we can use our mole to mole ratio to solve for moles of copper. So for every 1 mole of hydrogen gas, which I got from my balanced equation, I get out 2 moles of copper solid, which I also get from my balanced equation. So I'm going to take that 11 and I'm going to multiply it by 2. And we get out 22.3068 moles of copper. So that is step 2 complete. Our final step is to convert moles of solid to mass. And since we're just looking at copper solid, it's just going to be the molar mass of copper from the periodic table. So we're going to multiply this by 63.55 grams in 1 mole. Oops. 63.55. There we go. There, 63. So we get out 1,417.59 grams of copper. With sig figs, this would be 3 significant figures, so we would have 1.42 times 10 to the 3rd grams of copper as our final answer. So from 250 liters of hydrogen gas, we would produce 1.42 times 10 to the third grams of copper. We can also use this concept to use partial pressures to solve problems. So when we're in an actual laboratory and we want to determine the volume of gas that can be produced from a chemical reaction, like the one we just saw, the volume of the gas can actually be recorded by trapping that gas in a piece of glassware that can measure volume, right? Volume can apply to liquids, but it can also apply to gases. You just have to be a little creative about it. So we do that by trapping the gas over water. So the volume of gas produced by a chemical reaction can be measured using an apparatus like the one shown below. So here we have the reaction happening. So here's where we start. The reaction is happening here. We have KClO3 reacting with MnO2. We're heating it up. And when we heat that up, we produce oxygen gas. So the oxygen gas goes into the air, okay, and goes up the little test tube here. The test tube is attached to a tube, okay, and that tube runs underwater into a graduated cylinder. So the oxygen gas, I'm going to mark it in red now, continues through that tube, okay. The cylinder was initially filled completely with water, okay, but as the oxygen gas goes up, it's forming bubbles and it's displacing that water. So we're going to continue to displace that water with the oxygen gas that's produced from the reaction until the reaction is done. Once the reaction is complete, we can measure the volume of gas in that graduated cylinder and say that that is the volume of gas that was created from that reaction. The issue here is that these bubbles right here are going through water. And as they go through water, they actually take on a little bit of water. So the gas that's in here is actually mainly oxygen gas and some water vapor. So when gas is collected over water in this manner, the total pressure of the gas in the cylinder is the sum of the two partial pressures. Those partial pressures being the collected gas, which is in this case the oxygen, as well as the pressure of the water vapor. Now the idea here is that if we know the volume of the gas and we know the pressure of the gas, we can find the moles of the gas, which could then tell us the moles of reactant that we used in the reaction. So we have to be able to know the exact pressure of the gas that is not mixed with water. So to do that, we have to know the water vapor pressure. So the vapor pressure of water is known at various temperatures. At 0, it's 4.6. At 15, it's 13.64. At 45, it's 72, and so on. So the vapor pressure of water is going to vary at different temperatures. More water will come out of that solution the higher the temperature is. But this means if you know the total pressure and the vapor pressure of water, you can then find the pressure of the gas by itself, because P total is going to be equal to P gas plus pH2O. We know this, we can measure both of those, meaning we can find that. If the pressure of the gas is known, along with the volume of the gas collected and the temperature that it was collected at, we can use PV equals nRT to find the moles and even the mass of the gas formed. We could also go back to product and see, or go back to our reactant and see how much reactant we used. We could do so much stuff just by finding the moles of gas for that reaction. So let's try that for the reaction that we just saw. We want to calculate the mass of oxygen produced by the decomposition of KClO3 when 821 milliliters of oxygen is collected over water at 30 degrees C and 1.015 atm. So the first thing that we're going to want to do is realize that this was collected over water at a specific temperature. This tells us that we have to use P total equals P gas plus PH2O to solve for P gas. So the total temperature was 1.015 atm, and at 30 degrees Celsius we can find the vapor pressure of water from our table. So 30 degrees Celsius, we have a vapor pressure of 31.9 torr, right? 30 degrees Celsius, here's temperature, here's pressure, 30 degrees Celsius, 31.9 torr. So we have 31.9, there we go, 31.9 torr. I have to convert torr to ATM, okay, because I can't use torr as my pressure unit if I'm going to use ATMs. So we're going to use our conversion factors from our previous lesson. Where 1 ATM is equal to 760 torr. So we'll take that 31.9 and we will divide it by 760. So we get P gas is what we're looking for, and the pressure of the water is 0.0419. You can throw 7 on there, why not? So in order to find the pressure of the gas by itself, we take 1.015 and subtract off 0.04197 to get the pressure of the gas is equal to 0.97303, and that's all in ATM because that was an ATM. There we go. So now we have our pressure of the individual gas, we have our volume, and we have our temperature. So we can now solve for N. We're going to just quickly convert milliliters to liters, 0.821 liters, so that we can use R appropriately. But we get P of 0.97303 times the volume, 0.821 liters, is equal to N, which we're solving for, times R, 0.08206, times the temperature, 30 plus 273.15. So we solve for N by doing 0.97303 times 0.821, and we divide that by R and the temperature. So we get an N value of 0.0321 moles of, not KClO3, of O2. We wanted to find the mass, so now all we have to do is multiply by the molar mass of O2. 1 mole of O2 is 32 grams. So we'll take that and multiply it by 32. And we get a total mass of 1.03 grams of O2. 3 sig figs there. So that is the mass of oxygen produced from the decomposition of KClO3. Let's do one more. Determine the volume of gas collected over water when 0.501 grams of oxygen is produced by the decomposition of KClO3 at 35 degrees Celsius and 1.08 atm. Okay, so the first thing we're going to want to do, it's collected over water, so let's solve for the pressure. P total is equal to, here we know P total, we'll just write that, we don't need to write the whole equation out. P total is 1.08 atm. We want P gas, so we need to find the vapor pressure of water at 35 degrees Celsius. Water, 35 degrees Celsius, we have 42.2 torr, which we're going to divide by 760 to get atm. So 42.2 divided by 760, just like we did in our previous example, is 0.0555 atm. So we'll use that as our pressure for water. So our pressure of water, 0.055. So to find the pressure of the gas, we do 1.08 minus that pressure of water. So we get P of the gas is equal to 1.0245 atm. Okay, so now we have the pressure of the gas. That's fine. This time we're going to work a little bit backwards. We're given the mass of the oxygen. We now want to work backwards to find the volume of the oxygen. So we're doing the reverse of what we just did. So let's look at what we just did. We had the mass. We're going to use the molar mass to convert to moles. We'll use that and plug it into PV equals nRT and solve for volume. So let's do that. We have 0.501 grams of oxygen, which we are going to divide by 32, so grams cancel and we're left with moles. So we get 0.01565 moles of O2. Now that we have moles of O2 and the pressure of that gas, we can plug that into PV equals nRT, where pressure is 1.0245. The volume is what we're looking for, and we just solved for 0.01565. R we already know, 0.8206 because we're in ATMs, and the temperature is 35 plus 273.15. So we're going to take that moles, 0.01565, multiply it by R, and multiply that by the temperature, 35 plus 273.15. We'll divide that by 1.0245 so that we can isolate the volume by itself, and we get a volume of gas of 0.38627 liters. So typically this would be recorded in a lab setting, and graduated cylinders are measured in milliliters, so we can convert this to milliliters by multiplying by 1,000. And we get, with 3 sig figs, 386 milliliters of O2 gas collected. Okay, so that's our way of using PV equals nRT, as well as our concept of partial pressures, to come together and determine either the volume or the mass of a gas that is collected over water. That completes our last lesson of Chapter 11, so please complete your ALEKS homework for this lesson.